Thank you for introduction. I'm Jaehwang Jung from KAIST. Despite this talk being the managed language session, actually I'm going to talk about the problem of concurrent memory reclamation in unmanaged languages like C++ and Rust. And then I'll introduce our new automatic solution named Concurrent Immediate Reference Counting. So let's consider a linked list like this. Suppose the first thread, T1, loads a reference to node 1 and is about to access it. But the scheduler stops T1 and runs the second thread, T2, who wants to remove node 1. If we're not considering concurrency, T2 will simply unlink the node 1 from the list and just free it. But in concurrent programs, it's not safe to free the node immediately, because when T1 wakes up, it will access node 1, which is an user after free error. So to safely free node 1, we should wait until T1 has finished accessing node 1. Solutions to these problems are usually called safe memory reclamation algorithms, or in short, SMR algorithms. There are several approaches to this problem, but they are either difficult to use, slow, or their memory usage is not stable. In this work, we developed Concurrent Immediate Reference Counting, or CIRC, which is easy to use, fast, and shows a stable memory usage. But before getting into CIRC, let's review some existing methods that CIRC builds on. First, let's take a look at epoch-based reclamation, or EBR, which is a manual SMR method. In EBR, we should first activate a critical section before starting an operation. It doesn't provide mutual exclusion like lock critical section, but instead it protects the thread's local references in the sense that it prevents the reclamation of the objects that this thread can reference. After we remove a node from the list, we should use the retire function to schedule the reclamation of the node, and this reclamation is deferred until all the current critical sections are released. This ensures that the threads can safely access their local references inside their critical section. Using manual methods like EBR can be quite difficult because the user has to call the retire function manually. Specifically, to retire an object, it should be first made unreachable from the shared data structure. But reasoning about this object reachability in non-blocking concurrent programs can be really complex. So the reference counting is an easier alternative. Its interface is so simple that it can be automated using smart pointer types. For example, here we have an RC, which is the type for the pointers that are backed by a reference count. And there is an atomic RC, which is for the shared mutable locations containing an RC. When you load from an atomic RC, the counter is incremented. And when you update its value, the old reference is decremented and the new one is incremented. And we remove a reference, then the counter is decremented. Finally, when the count reaches 0, the destructor of the object triggers recursive decrement of the successors. The problem of reference counting like this is that it's very slow. This is because getting local references is really frequent operations. For example, when you're traversing a linked list, and each of these local references incur a high overhead because you have to atomically modify the reference count. So deferred reference counting algorithms optimize these local references by combining reference counting and the manual method under the hood. There are several approaches to deferred reference counting, such as CDRC, OrcGC, and FRC. And in fact, our algorithm CIRC is based on one type of deferred RC. So let's take a look at our approach. In deferred reference counting, the local references are not counted by default. Instead, they use the faster protection functions of the manual method, for example, EBR's critical section. And to ensure the safety of local references, destructing an RC uses deferred jobs. Specifically, our version first decrements the count, and then if the count reaches 0, then it schedules the deferred reclamation. So the object can be freed when the critical sections are released. Deferred RC is fast and convenient, but when using them, the garbage objects can pile up and it can result to a big memory usage, huge memory usage. This data from our benchmark for log-free queue using CDRC shows that the memory usage can keep growing over time, while on the other hand, the memory usage of the EBR version is stable. The reason is that the execution of the deferred jobs can lag behind the creation of garbage. For example, suppose we rapidly remove the nodes from the head of the list, like this. And then after some delay, the first node is going to be reclaimed. And then after another delay, the second node is reclaimed. And after some another delay, the third node is reclaimed, and so on. So this delay between the reclamation of the linked nodes results in a big pile of garbage that takes a very long time to reclaim. Our new algorithm, CIRC, fixes this problem. As I mentioned a while ago, CIRC is actually kind of deferred reference counting, but it handles this garbage chain by making things more immediate. Specifically, the key feature of CIRC is to allow immediate recursive reclamation of the garbage chain. This means that when we reclaim the node 1 and decrement node 2 as a result of that, we should be able to immediately reclaim node 2 without delay and do it recursively for the rest of the nodes. To do this safely, we should check that they don't have local references, which is why the deferred RC algorithms are slow at freeing big garbage. So our challenge is how to efficiently check whether the successor nodes have a local reference. The key idea of our solution is that we can detect local references by looking at the timeline of the events. Let's consider a scenario where the successor of the reclaimed node has a local reference. Suppose the node 1 is popped, then T1 enters critical section, and where it loads a local reference to node 2, and then pops node 2. Now, just by looking at the timeline of the events and the reference count, we know that T1 cannot have a reference to node 1 because T1 enters critical section after T1 reaches 0 count. So we can free node 1. But can you free node 2 right now? The answer is no, because node 2 is popped after T1 entered critical section. So T1 may have a local reference to node 2. So to implement this idea efficiently, we're going to use the epoch clock from the EBR. And in EBR, we have a global epoch clock that represents the logical time like this. And the thread can start a critical section at some epoch E. The key property of this epoch clock is that it increases to E plus 2 only after the critical sections that started at epoch E are released. This means that there is a causality between critical sections of epoch E and epoch E plus 2, but not necessarily between E and E plus 1. CIRC uses this epoch clock to track the epoch of each decrement, and it reclaims the 0 count objects. This is done in 3 steps. First, when decrementing, we are going to record the current epoch in the object. And second, we're going to use this epoch to check the safety of executing the deferred reclamation. And third, when you decrement the successor of the reclaimed object recursively, we'll record an epoch. But instead of using the current epoch, we're going to use an old epoch value that is derived from the epoch of the predecessor, so that the successors can be reclaimed immediately. Let's take a deeper look at each step. The last decrement epoch of the object is stored next to its reference count so that it can be atomically updated together with the reference count. And when decrementing an object non-recursively, we update the decrement epoch to the max of the previous value and the current epoch, so the value does not decrease. We can use this decrement epoch to check whether it's safe to free a zero count object. Suppose a thread at epoch E decremented an object to 0, or in other words, it destroyed the last RC reference to the object. Then a thread at epoch E plus 2 cannot load a local reference to the object because of the causality. But on the other hand, a thread at epoch E plus 1 may load a local reference from the last RC because it can run concurrently with epoch E. At epoch E plus 3, we can reclaim this zero count object because since at this point, no one can have a local reference to the object. The recursive decrement is a bit more complicated. Suppose we are decrementing node 2 as a result of destructing node 1. According to the rule we saw a while ago, we may update its decrement epoch to the max of the previous value and the current epoch. This is safe, but it prevents the immediate recursive destruction of node 2 because we have to wait at least 3 epochs to free node 2. So instead, we should find a smaller epoch x such that it's safe to pretend that this decrement happened at epoch x in the past, so that it leaves a possibility of reclaiming node 2 right now. This problem boils down to finding the last epoch when this RC reference can be accessed. We need to consider 2 cases. In the first case, this RC reference to node 2 can be accessed through a reference to node 1. So we should consider when this node 1 can be last accessed. This is simple because it's already tracked by the node 1's decrement epoch. So the updated decrement epoch for node 2 should be at least E1. Second, we should consider the case where this RC reference to node 2 was initially owned by a thread and then stored into node 1 at epoch E link. Then we can consider an epoch timeline like this. Interesting thing, so we can consider an epoch timeline like this, and epoch E plus 2. We know that there is a no owning thread we know that no thread owns this RC. But at epoch E link plus 1, there can be another thread that previously owned this RC and then passed it to the storing thread. So the decrement epoch of node 2 should be at least E link. So since we have to use this value, we're going to record it along the pointer when it gets stored into node 1. In conclusion, we can update the decrement epoch of the successor to the max of previous value and the decrement epoch of the predecessor and the link epoch. According to the epoch rules, this object can be reclaimed 3 epochs after that. But if this link is a part of a big garbage chain, this new value is likely to be equal to the predecessor's decrement epoch, which means that node 2 can be reclaimed right now, which enables immediate recursive destruction. So that was the key idea of CIRC. Our experiments show that the memory usage of the queue using CIRC is similar to that of the EBR version, and it's as fast as EBR in read most cases, and it introduces only a minor overhead in the write-heavy cases. In summary, CIRC is an automatic SRM method, which uses reference counting that is fast thanks to EBR-protected local references, and at the same time is able to quickly reclaim garbage. Please take a look at the paper for interesting details like optimizations and how we handle increment from 0. Thank you for your attention, and I'd be happy to take any questions.
Okay, we have time for one question or two.
Hi, thanks for the talk. That sounds quite cool. So I see the Rust logo here, so I take it you've implemented this in Rust.
Yeah, in fact, it's published in crates.io.
Okay, awesome. So I wonder, is it an entirely safe to use API, or does the user have to worry about, like, have to use unsafe blocks somewhere because they need to get something right with respect to these critical sections for the epochs and things like that? Because I recall previous approaches to safe memory reclamations in Rust didn't have entirely safe APIs, so I may be out of date there.
Right, it's a great question. Thank you for the great question. For the usage itself, most of the API are safe, but there's some shortcut API like dereferencing or reference without null check that is obviously unsafe. And there's an important detail here is that you have to implement an unsafe trait to identify the atomic RC fields inside the object so that you can, this kind of, they can be annoying, but it's a very straightforward implement.
Could this be automated with like a derive macro or something, and then I don't have to worry
Yeah, it can be
about
derived. Yeah, right.
Okay, cool, thanks.
Great, thank you.
I do have one question. The previous speaker used static analysis to try to figure out when things could be heapified. Could you figure out or use a static analysis to try to figure out when something will obviously become garbage and you would skip all of this at runtime?
In concurrency, that's not really possible. So actually, we try to find some type-based some method that uses smart pointer types to do some even more optimization, and we found out that that's actually unsound. Yeah, so I think there's a little room for static analysis.
Okay, thank you.
Great.
Okay, that's it. Let's thank our speaker again.
Thank you.